How do op-amps perform integration? We know that operational amplifiers are used to implement different mathematical operations. Simple operations are achieved using common op-amp configurations. For example, addition is done by the summing amplifier, subtraction by the difference amplifier, sign changing by the inverting amplifier, and so on. But calculus? How is this achieved in a circuit? Let's discuss the op-amp integrator, which should be familiar to you in terms of the setup. It looks very much like the typical feedback configuration, except we have a capacitor instead of the feedback resistor. Let's analyze this circuit and understand how integration is achieved. Any ideal op-amp is governed by two constraints. Vp, the voltage at the non-inverting input, is equal to Vn, the voltage at the inverting input. An ideal op-amp is assumed to have infinite input resistance, so the second constraint is that no current enters either terminal of the ideal op-amp. Notice that the non-inverting terminal is directly connected to ground, meaning Vp must be equal to 0. By the first constraint, this must be Vn as well. With this information, let's apply nodal analysis at this node over here. We'll write a KCL equation. Notice that this is directly connected to the inverting input, so the voltage there is of course Vn. Let's call the current through the resistor IR and the current through the capacitor IC. By the second constraint equation, we know that no current enters the inverting input, meaning that IR must be equal to IC. By Ohm's law, we know that IR is the voltage across the resistor divided by the resistance. This will be Vi minus Vn over R. So, let's replace this instead of IR in the equation. IC, the displacement current of the capacitor, is the capacitance times the derivative of the voltage across the capacitor. So, let's replace that as well. What is this Vc? What is the voltage across the capacitor? Looking at the circuit, this is obviously Vn minus Vo. And now let's use our knowledge that Vn must be 0, because remember, the non-inverting input is grounded, so if we substitute 0, the equation simplifies to this. Derivatives are linear operators, so we can take the negative outside, like that. And now let's solve for the output voltage Vo. We can cross-multiply, giving us dVo equals negative 1 over Rc Vi dt. And now we can calculate Vo by integrating both sides. The integral of dVo is just Vo. Negative 1 over Rc is a constant, we can take it outside. And now we're integrating the input voltage Vi. You may be thinking, is this an indefinite integral? Actually, it's a definite one. The bounds go from 0 to t. So we're accumulating the input voltage from the moment it was applied up to the present moment t. Technically, we shouldn't have t in the bounds as well as dt as the variable of integration, so we're going to change it to a dummy variable. Call it tau. So we're going to integrate Vi of tau d tau from 0 to t. By the fundamental theorem of calculus, this will give us Vo of t minus Vo of 0. Think of it as integrating Vi and then plugging in the bounds, t and then 0 and then subtracting them, correct? Now, this negative Vo of 0 is basically the initial voltage across the capacitor. So, it is important to ensure it is discharged for this Vo of 0 to vanish in the equation. Assuming that the capacitor is indeed discharged at the moment of the application of the input signal, we can assume this is 0. With that, we see the relationship relating the output to the input. the output voltage is a weighted integral of the input signal. Say for simplicity R is 1 kilo ohms in the integrator circuit and the capacitance is 1 millifarad. Then, if the input voltage is a pure cosine, the output voltage would be a negative sine of the same strength.